So let's look at the electromagnetic spectrum. Recall from last time that electrons exist in certain energy levels. They can only move from one energy level into another if they have a specific energy. So in order for it to transition from one energy level to another, it must absorb a certain amount of energy, or it must lose a certain amount of energy. This energy that is, whenever it falls down, the energy lost usually is in the form of an electromagnetic wave. The electromagnetic spectrum is the complete spectrum or continuum of all forms of light. An electromagnetic wave consists of electrical and magnetic fields which vibrate, thus making them waves. Vibration is oscillation, back and forth motion. From physics, the only thing from physics you should know is, don't really need this, but if a electromagnetic field, or if an electrical field changes, it creates a magnetic field. If a magnetic field changes, it creates an electrical field. So if we have a constantly changing electrical field, it'll create a changing magnetic field. And that changing magnetic field will thus create a changing electrical field. And this will continue to, the electrical field will create the magnetic field, and the magnetic field will create the electrical field. And this will continue for all eternity, unless it's somehow stopped by the wave hitting some object and getting absorbed. But that's all a piece of light is. And it just so happens that the electrical field is changing, creating a magnetic field that changes, and it's just a never-ending cycle of itself creating itself. And it propagates out into the universe. So we break up the spectrum into various sections. The ones with the lowest frequencies are called radio waves. The next one is not cell phone, put microwave. Or I guess omit cell phone waves. There is no such thing as a cell phone wave being a proper thing. Cell phone, so I won't say this about microwaves. Some places say microwaves is a subsection of radio waves, so they break radio waves apart. For example, they often say your cell phone uses radio waves, but technically it's in the same section as microwaves. Microwaves are going to be the gigahertz terms of frequency. Oh, and that's the last. Yeah, never mind. Right. Then we have. Why in the world? Okay, ignore radar waves too. I did not remember this PowerPoint including all these. I think I edited it and saved it somewhere else. The only ones you need to know is radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma. Radar and cell phone are most definitely not official waves. It gives you a perspective of where cell phones and radar actually is, though. Cell phones sit closer to the microwave and radio wave spectrum. The boundary of what a microwave and what a radar wave is kind of loosely. There's no magical number. that this is most definitely a radio wave, like the boundary in between radio wave and microwave kind of bleed into each other. Cell phones are on the low side of microwaves or the high side of radio waves. Radar is a little higher than microwaves and infrared. It's lower than infrared. And if we were to look at the frequency, so radio waves have the lowest frequency. Then we have microwave has higher frequency than infrared, than ultraviolet, and gamma has the highest frequency. So it goes radio, then microwave, then infrared, visible, ultraviolet, and X-rays in between ultraviolet and gamma. So waves are properties of electromagnetic waves. So properties of electromagnetic waves include their speed, their frequency, and wavelength. I use the letter V for velocity instead of speed. Speed, I use the letter V referring to velocity, so this equation is going to be slightly different than a PowerPoint. Mathematically, it makes no difference what letters you use. Frequency is a lowercase f. Don't use capital. And wavelength is the Greek letter lambda. It's a lowercase l, but in Greek. So the equation I use is V equals F times lambda. So the speed of a wave is going to be equal to the frequency times its wavelength. All light waves travel at a speed of approximately 3 times 10 to the 8 meters per second in a pure vacuum. Getting into physics a little bit, light can actually slow down when it transverses into a medium. So light travels slower in water than it does in air. But for the most part, we're going to assume that we're in a pure vacuum. It doesn't slow down much in air, so in air is good enough approximation. 3 times 10 to the 8 is the speed of light. Approximately is actually 299,900 and something is very close to 3 times 10 to the 8. So all parts of the electromagnetic spectrum travel at the same speed. Radio waves move at the same speed as gamma rays. Visible light moves at the same speed as microwaves in a vacuum. And for all purposes, I'll assume vacuum is going to be the only thing we're looking at. Therefore, wavelength and frequency have this indirect relationship. So the speed of light, which is usually represented with C, let me just... So I write the equation as this. V is equal to F times lambda. If you can't make this fancy letter like this, even this is not badly drawn, you could simplify it and do this. So this is speed or velocity. This is frequency. And this is wavelength. Speed and velocity is always going to be measured in meters per second. Frequency is a hertz. And if you don't know what a hertz is, it's 1 over a second. It's an inverse second. Seconds to the negative 1. And wavelength is in meters. We have the speed of light. Speed of light is equal to 299,792,458 meters per second. Bless you. This is constant. No matter where you're at in the universe, no matter what speed you're traveling at, this is always the exact value. We got it. This is the definition of a meter in a second is defined precisely, so this is exact. We can round this though and say that C is approximately, and if you've never seen this notation, the squiggly equal sign is approximate 3 times 10 to the 8 meters per second, and this is the value we'll use in this class. So for a EM wave, the equation simply becomes C equals frequency times wavelength for EM waves in vacuum. Everyone good? So let's do an example. Does anyone know the frequency of the microwaves generated by a microwave? You ever looked on the side and see what frequency it actually generates? I have this memorized, but I'm going to double check. It should be 2.45. So microwaves use yeah.
The machine out all the time, but be sure and buy it during your lunch break because for the lunch line, it's bottle of water for the day.
For all commercial microwave ovens, generate microwaves at 2.5 gigahertz. Why do they do this? Does anyone know how a microwave heats your food? Does anyone know? Let's look at a swing. So let's say that we have a person on a swing and we have another person who is pushing them. So they're pushing them this way. How can you make a person swing higher and higher and higher? When should you push them? Should you push them when they're in the very bottom, moving towards you? Well, that causes them to stop, wouldn't it? Should you push them at the very bottom whenever they're moving away from you? Yeah, that'll speed them up. Should you push them like this? When they're at the top, when they're stopped? Yeah, kind of, that'll speed them up. But if you look at the best way of doing it, it's whenever they're at their maximum point closest to and they're about to move to the right. So if someone is swinging back and you give them a tiny little shove, they'll go to the right, they'll swing back, go to the left, and you push them again right at the perfect moment, they'll go with more higher speed, right? If you keep pushing them when they keep coming, they'll come back to you higher and higher and higher. Eventually, if you're there is some friction involved, the friction would eventually cause them to slow down and come to a stop. But if there was no friction and you keep pushing them when they're at this point right here, they would eventually start doing circles around. You would keep adding energy into the system. So let's look at a water molecule. Water molecule has an oxygen attached to 2 hydrogen atoms. And what is this angle? This angle between the two hydrogens is 104.5 degrees. And what would happen is if a microwave were to come in and hit this hydrogen atom, well, the hydrogen atom is going to bounce closer together. And it's going to end up pushing this one to the right. And because this is positive and that's positive, they're going to repel each other. So this one's going to swing backward. And if right at the moment it swings back here, I hit it with another microwave, like a person on a swing set. I'm going to hit the hydrogen atom. It's going to bounce back this way. And then it's going to get closer to this hydrogen atom, and it's going to want to bounce back this way. What a microwave does, is designed for water at this frequency, is it's causing the 2 hydrogen atoms to vibrate back and forth. And what is temperature? Temperature is the average kinetic energy, or the average motion of all the particles of a substance. So if we cause these 2 hydrogen atoms to vibrate back and forth, we're increasing its kinetic energy, and hence we're heating up the water. That is how microwaves work, is all we're doing is causing these 2 hydrogen atoms to vibrate in place. And you can think of it exactly like a swing set. You push on it when it's at the highest point, it pushes it to the right, it gets closer to this positive one, which causes it to repel and bounce backward, then we push it again. Technically, 2.45 gigahertz is not the correct frequency. It's slightly wrong. We do not want to push on it at the right time, at the perfect time. If we were to push on it when it's at the highest peak right here, all the microwaves would be absorbed on the first layer of water. And that would mean that if you put in, let's say, some frozen, like a frozen piece of meat, you would boil the water and moisture on the surface while the inside of it would be completely frozen. We design microwaves to be very slightly off of the optimal frequency that water vibrates at, off of the resonant frequency of water, so that some of the microwaves will slow down so that the outside doesn't boil before the inside cooks. Anyway, if we look at this 2.45 gigahertz, giga, so this is gigahertz. Giga means 1 times 10 to the 9. So 2.45 gigahertz, it's the same thing as 2.45 times 10 to the 9th, or billion. It's a billion hertz. By the way, a megahertz is 10 to the 6, and a kilohertz is 10 to the 3, or 1,000, so 1,000, a million, a billion. So we use our equation. C is equal to F times lambda. We can solve for the wavelength. So C divided by F is equal to lambda. Or speed of light is 3 times 10 to the 8 meters per second. Or frequency is 2.45 times 10 to the 9th hertz. A hertz is really a divide by a second. So divide by a second divided by or a per second divided by per second cancels each other out, giving us just meters. And that's equal to 0.12244,898 meters, which is approximately 12.245 centimeters. Which, if I divide that by 2, that's 6.1. This is to scale. This is literally the dimensions other than amplitude of a microwave that is found in your oven. So this is 1-to-1. So wavelength is the distance between two identical points. So note that it's sloping downward right here, and it's sloping upward right here, so these two are not identical. But from this distance right here to this distance right here is one wavelength. This top portion is called a crest, and this bottom portion is called a trough. But if I measure from crest to crest, is also a wavelength. So another definition is crest to crest distance, or trough to trough. Amplitude is from this middle line up to the top of a crest. It's called the amplitude. It's a measure of energy. So amplitude is from midline or midpoint to top of crest or bottom of trough. So, light, which microwave is a form of light, can bounce off of surfaces. So if we have a microwave, what happens inside the microwave is we have a little opening here, and the microwave gets generated inside the oven. It hits the side of the wall, and then it bounces back. Notice how I'm drawing it bounce back. It bounces back such that it amplifies itself, getting stronger and stronger and stronger. This is known as a standing wave. So it looks something like this inside your microwave. It comes in, strikes the walls through their specific shapes and sizes, hits the side of the wall, and then bounces back, hits the other side of the wall, and then bounces back. Where do you think your food is heated the strongest at? At the point where the amplitude is the highest. Your food is heated more in the center. At this point right here, and at this point right here, and at this point right here, your food does not get heated at all. I want you to note that this is the actual size of a microwave in your oven. This is two overlapping. If you remove the turntable, the rotating table from your oven, some ovens don't even have turntables. My first oven, whenever I was growing up, didn't have a turntable. Do you know how we had to heat up food? We put it in for 30 seconds. We then take it out and we put it in a random place. We heat it for another 30 seconds. We stop it and move it around. Because if I can get some shredded cheese and remember it, we're going to go in there and do this. So this right here, this distance from here to here would be half a wavelength. And we're going to actually see where cheese melts. We'll have these little corners where cheese is completely not melted. Then we'll probably have burnt cheese right here. And then we'll have, so this region will probably be super burnt. This region will be melted. And right here, completely still cold. But we can take the midpoint between two unmelted places and actually measure the wavelength of microwaves in the oven. Almost all microwaves operate this frequency because it's designed to allow microwaves to evenly heat up your food. But note that if you were to put, this is the reason why I don't know if y'all do this. I know to make sure I do this. Do y'all you want to put your food on the outer turntable so that it actually moves a lot. Because there are if you were to remove your turntable and put it in a square plate, what would happen is molten here, uncooked here, molten here, molten. So the places I'm coloring is the only spots it really heats up. That means that if you were to, this spot right here would be completely still frozen. So that happens two reasons. One, ice has a different crystal structure than water. If you put ice cube in the microwave, ice cube won't heat up. If it's completely 100% frozen. It will some degree, but the moment it starts turning into water, the water molecules can now vibrate freely. And then vibrating water molecules is going to superheat up and melt the rest of the ice. So what you're going to have is, imagine you can have a perfect cylinder of ice. So you have a block of ice. Initially it starts melting. This water is going to get super hot. It's going to start melting this ice. this is now going to start heating up this, and it'll melt like that. Ice does heat up in a microwave, but not as much as water. A microwave is specifically designed for the idea of vibrating the water molecule. Some ceramics have a close enough structure. If you've ever put ceramic bowls and touched them and they're super, super hot, that's because the chemical structure of ceramic is close enough. Again, we don't match up we don't want it to be the true frequency. So this is called, there's a certain frequency that is known as a harmonic frequency. Have you ever seen the videos of people like shouting at a wine glass and it breaking? That's the same idea. There's harmonic or fundamental frequency.
Excuse me, teachers, we need to at this time, be sure to check your emails. Ms. Lee sent out an important email yesterday about regarding an update that Region 7 has done.
I did not already.
Please check your emails and respond to that. Thank you.
There's a certain frequency at which things like to vibrate. If you have a tuning fork, you hit it, them two leads will vibrate back and forth. So if you have a tuning fork that looks something like this, based on the shape of the fork, how long these are, they want to vibrate back and forth at a certain rate. A wine glass has a shape like this. This, based on the circumference of this, and the material glasses out, there's a certain frequency, fundamental frequency, that it likes to vibrate at. If you were to match this frequency, you create something known as a standing wave. This is a standing wave, where it will go down here, hit the wall, or hit itself, and then be reflected back into itself. Meaning every time you add another wave to it, it just amplifies. Let me show you a video of standing waves. But you don't want microwaves to be perfect. Otherwise, you'll boil the outer surface of whatever you're trying to cook while the inside stays frozen. That's the reason why Hot Pockets. Wait, I should go back. That's the reason why Hot Pockets usually the inside is still frozen, while outside is burnt. Especially if you don't move it. There's two things going on, or multiple things. One is your microwave only really heats up certain areas. There are dead spots in between it. This is also in 3D. So in between the So right here, no heat. Right here is where the highest heat is. At this point right here, no heat. Right here, max heat. The next thing is if you have a medium and a microwave comes in. So a microwave, how it's heating it up is it's literally being absorbed by the electron on the hydrogen atom. So it's coming in and it's being absorbed by this hydrogen atom. It transfers this kinetic energy into this hydrogen, pushing it. Which hydrogen atom do you think you'll hit first? The water molecule at the surface or the water molecule at the very middle? In order for it to hit the one in the middle, it has to completely miss all water molecules and randomly hit this one. You have to remember that if you were to shrink down an atom, what's the scale? So if you were to shrink down an atom to the size of a football stadium, the nucleus is the size of a marble on the grass. So it's over 99% empty space. The chances of an electromagnetic wave actually colliding with anything is low. But you also have to remember there's an Avogadro's number of atoms in every gram of substance. So there's a lot of atoms, but it's mostly empty space. So when you shine light on, let's say, a wall, chances are the light is not going to be stopped by the first atoms. Some of it will, some of it won't. Some of them will go through. There's quantum mechanic things. The electrons are generating their own electrical field interactions with the electromagnetic wave coming in. Getting all complicated. But what happens is you want the electromagnetic wave to not perfectly match this frequency, so that whenever it occasionally absorbs into the outer layer, it'll occasionally cool it off. Did y'all know that microwaves can be used to make things cold? The most coldest temperature we ever received, or created on Earth, is a billionth of a Kelvin. We did it with lasers, basically like microwaves, shooting microwaves. So imagine you have an atom, and it's moving in this direction. If we shine a laser at it, we can make it change direction and go like this. If it's coming toward us, we can send another laser light toward it and eventually get it almost stopping. Or another example would be that it just starts slowing down like this. Again, we're transferring the energy of the light into the material, and we can cause it to change what direction it's traveling in. Light has momentum, and that's how this works. The reason why water heats up almost always is because we're creating this oscillation right here. Some of the time, so again, if we have it not on the right frequency, some of the time the hydrogen atom will be moving in this direction, and the microwave comes in and hits it from this direction and slows the hydrogen atom down, and that's what makes it get colder. But we have it very closely matched so that the number, I think it's like 80% or 70%. 70% of the time or 80% of the time that EM wave, a photon, hits hydrogen atom, it heats it up. The 30% of the time or whatever, it cools it off. So overall, most of the time it's heating it up, and this is so that they'll randomly get in and heat the middle. Some things are transparent, so the glass is transparent to visible light. That glass is opaque, meaning it blocks infrared. Let me show you water. Very low quality video. So all this is doing is it has a perfectly close enough calm bed of water, and on the other side it's pushing the water, creating a wave. So it's going to start here in a second. It's going to start moving back and forth. There it goes, creating waves. And the waves are going to hit the back wall, the wall closest to us. And then they're going to start moving in the opposite direction. If they perfectly match up, they'll create something known as a standing wave. It's where the crest of one wave that's going forward lines with the crest of a wave that's getting reflected back, and they combine, making a bigger wave. And note how tall the waves were at the beginning versus how tall they are now. Every wave the one on the back generates increases the amplitude here. if you were to keep doing this, eventually it would probably start flashing out. There is some loss due to there's some loss due to friction. Some of the energy and big amplitude is energy, the height of the wave. But that's the reason why a wine glass breaks. If you're at the fundamental frequency and you were to keep adding that wave, so what happens is if you currently have this wave in a system and you were to send at the exact same time another wave, what happens is the crest of this one and the crest of this combine and it makes a bigger wave. This is known as constructive interference. We're not going to get too much into this. I'm trying to teach you a little physics. So if you add this plus this, you get a bigger wave. If you do this and then the opposite, you actually get cancellation.